So we say plot okay. So you see that this is a ECG clean signal. So that it looks like. But how about the raw signal? Is there any trace whether there is an ECG? Hardly you can see that, right? Very, very noisy, right? Do you agree?
Yes, sir.
Okay. So next will be, I mean, we understand that it is indeed very, very noisy, and we have to somehow extract these information, these ECG, or they call ECG QRS complex, because there are certain points in ECG cycle which they call ECG QRS complex. Okay. So we have to basically extract very noisy signal, right? So now we have seen that they are very different, very noisy, and we cannot decide anything on from the time domain signal. What should be the next step? Yeah, let's try to do domain. Okay. So one way is that you apply FFT and then plot the FFT magnitude response. I mean further length. If you want to find out the signal power in frequency domain, the signal amplitude, you can also, I mean, plot the signal power in frequency domain. Okay. So for that, you need. So I do not know at the moment what is the sampling rate, let's say, but I can still be able to find out, hopefully. So we can use this P-Welch, this is a built-in function. So P-Welch is actually a power spectral density of any signal. Okay, through Welch, method. So Welch is the method, and P for power spectral density. Okay, or power of through Welch. So power spectral density, it means that power in a spectral domain, in frequency domain. So it takes a lot of input argument. Okay, but since at the moment we are not very sure about some of the input arguments, so when we are not sure, give the default value. Okay, so the best way to give the default value is that use a blank third bracket. Okay, so you see that the second one supposed to be a window, next one supposed to be the number of overlap, n overlap, and then number of FFT point. Okay, so these are the minimum requirement, and then also you need a frequency, I mean the sampling rate. Okay, so if you do not know anything about this, then you can simply do like this, and I have not given the sampling rate information yet. And if I plot this, let's see how it looks like. So it says that it is a Welch power spectral density estimate. Okay, in y-axis we have power normalized with respect to frequency, power per frequency. This is the normalized frequency with respect to pi. So this is power. We can think about power with respect to frequency, right? But this frequency is an angular frequency which is normalized with respect to pi. So what is pi? Pi is actually maximum amount of angular frequency, omega max. Okay, so if it is 0.2, it means that it is 0.2 pi. If it is 0.4, because it is already normalized by pi, so it only says 0.4. But if you want to get the real value of your omega, then you have to multiply with pi. So you see that normalized frequency, that means you have to multiply with pi. So zero point 0.4 means 0.4 pi, 0.6 means, so 1 means 1 into pi. That means the highest frequency is pi and the lowest frequency is 0, 0 into pi. Now this is your P wells or power spectral density for the which signal? Noisy or clean?
It's noisy.
So we want to also see how the clean signal looks like, okay? Because we have to do the comparison, otherwise we will not be able to find out where is the noise, right? So one thing is that I just want to change the color of this graph because I want to plot for the, so we have a different color, we can do the comparison and see the difference. It's taking a bit to edit the property of this graph. Okay, I think we should forget about this one for the time being. It's taking time. Say something more. Yeah, finally got this. Just wanted to change the color. That's great. All right, so now we want to plot the clean signal on the same graph. Okay. Okay. I think that now we should get back to this color. Okay. So what we have found here, the clean signal response is like this, right? And this one, the blue one, is actually the noisy one. Okay. So can you see something from this? So what do you expect now? What kind of filter you should use?
Low pass.
Yeah, low pass, but we have to find out the cutoff frequency now, right? The low pass. I wanted to make a zoom and I found that it is not available here. It was supposed to be here, but I cannot see the zoom in. I wanted to zoom in. Just anyway, so I cannot find the zoom in. Somehow this. Okay. So you tell me what is supposed to be the cutoff frequency of the low pass filter if I want to figure it out from here. What is supposed to be the cutoff frequency? So I need this part, right? Basically, and you see that this part are basically very low in power, so they are actually kind of noise. Okay. So what's supposed to be the approximate one? Okay, 0.1 pi. So that means, can we say that our omega c is 0.1 pi? From this, can we decide that our omega c is 0.1 pi? Yes?
Yes, sir.
Yes, sir.
So this, let's see, omega c is 0.1 pi. Okay, so 0.1 pi, we do not need to write down into pi. 0.1 means it is already 0.1 pi. Okay. Now, what are the other parameters required for us to design an IIR filter? If we know already omega c, what else I need to design an IIR filter?
Sir, A and B coefficient.
That I need A and B, but for A and B, I need to give that cutoff frequency and other parameter for. What is that? No?
Order.
Order of the filter. Okay, I have to give the order of the filter. Okay, so I do not know what exactly supposed to be the order, right? Okay, so let's say that I'm going to design an IIR filter because I have already got omega c, and if I just mention the order of the filter, then I'm supposed to have the other parameters, right? Okay, so let's say I have an order, let's say take fifth order filter. So for a fifth order filter, how many poles will be there? Do you remember how many poles will be there? It is actually k is from 0 to 2n minus 1, right? So how many poles will be there? Total poles?
4,
Nine.
sir.
Minus 1. Should be 9, right? Total pole, number of pole. And
Yes.
all the poles supposed to be, they must be on the left hand plane. If one of them is on the right hand plane, then I cannot use that because that it makes the filter unstable, right? Okay, so let's start with n equal to phi at the moment. Okay, so if I have omega c and n, is there any function I can use to find out the b and a coefficient? So in one of the last class, if you remember, we have talked about an user defined function which is already available in your lecture note. At the end of the lecture note, there are some specifications, right? There are some MATLAB example, right? So with that, can you use this some of this? Can you use this part to build the function? So because it's an IIR filter, so that means we have to talk about the analog loop, Butterworth prototype filter, right? So this is the Butterworth low pass filter prototype. Okay, if I give n and omega c, then I will be able to get b and a. I can use this function. It should work now. Our omega c is actually like this, omega c, right? And n is already we have defined. So now we got the b and a coefficient, right? Okay, now we have to find out how the filter actually looks like. We have to plot the magnitude and phase response, the frequency response of the filter. Okay, so we can, because it is a what kind of filter? Analog or digital? This Butterworth filter is analog prototype, so we use a freq s. Okay, freq s, a number of points, let's say 500 points. So this omega means the number of points. Okay, so let's see that how it looks like, the filter that we have designed here. So this is the filter that we have designed so far. Okay, so you see that this is the cutoff frequency. So where is supposed to be the cutoff frequency when my value is 70.7%, right? So let's say the y value is 0.784. That means around 70.7%, right?
Yes.
Or somewhere here, yeah. 0.69. That is approximately 70%. Y value is 70.7% of the maximum gain. So what is the maximum gain here? 10 to the power 0, right? What is 10 to the power 0? 1. So maximum gain is 1. And 70.7% means 0.7, right? So 0.69, can you consider this as 0.7?
Yes, sir.
What is my x
Yes,
value?
sir.
0.1. 0.1 frequency radian per second. Remember that we have talked about omega c as 0.1 cutoff frequency.
Yes, sir.
Yes. So this looks like a good low pass filter that which we can apply, right? How about the phase response? Is it linear or non-linear?
Non-linear.
Non-linear. Is there any discontinuity here? Sudden change?
Yes.
Yes. So basically this is the characteristics of your IIR filter, right? Having a non-linear phase response. Anyway, so let us get back to this part again. So apparently it seems that it is a good filter that we have designed so far, right? Yeah. Okay. So where were we? We were in the command window, right? Now what we have to do? We have to apply the filter on the signal, right? ECG raw. Okay. So for filter application, we have already a. So let's say that we call the output of the filter is ECG filtered, okay, which is equal to, we should be equal to apply the filter. So there is a built-in function filter, and all it requires is B, A, and X. I mean, these are the must value, input value B. So we already know what is B, what is A, and our X is, what is our X? The noisy signal. What is our noisy signal? ECG raw is our noisy signal, right? So we applied the filter now. So now we should be able to plot the signal. Yeah. We should now be able to plot the signal, right? So let us plot all the three signals: the noisy, the clean, and the filtered, right? So first we plot the raw signal, then the clean signal, then what? The filter signal. Okay. So is there any change? No luck, right? We have not been able to extract our AC signal yet. Okay, this is supposed to be the filtered signal, right? Okay. So what's the problem? What seems to be the problem? Our filter looks good, right? We have seen the magnitude response of the filter. It looks good, right? Remember?
Yes.
What's
Yes,
the
sir.
problem now?
Cutoff frequency.
I mean, yeah, so now let's plot the signal again in frequency domain to see that what exactly we have done. So maybe our filter did not work properly. Why? We want to know why. So the only way is that we know this is we plot the signal in frequency domain. Okay, remember that we did not know our cutoff frequency, I mean sampling rate, right? Sampling frequency was not given, and we did not use the sampling frequency yet. So maybe we need that sampling frequency information, otherwise we may not be able to design the appropriate filter. But let us first again try to see how the signal looks like in frequency domain, because what we have missed so far. Okay. You have plotted all of them in the same graph. So raw, then clean, then filtered. All right. So we have so these two we are already familiar with, right? And this is your filter signal. Okay. Now, don't you think that your filter signal, the characteristics of the filter signal seems to be very similar to this one?
Yes, sir.
That means the noisy signal still is the noisy signal. What is the difference? The power, right? Here the power is very low, minus 110 dB. Here the power is, minus 10 dB, something like that, right? So that means still we have not been able to remove this, the noise properly, right? Or our filter is not working, because we said that it was supposed to be a low pass filter, but somehow, the power in both the pass band and stop band is very low, right? So when you think about a low pass filter, we expect that in the pass band the power is highest, and the stop band it should be lowest, right? Okay. So, but we have designed the filter at 0.1 pi, angular frequency at a cutoff frequency, but still it is actually the similar thing. Okay. So, do you think that it might be because of the instability of the filter? Do you think that it can be a possibility? Because we have used IIR filter. Have we checked the stability of the filter yet?
No.
No, sir.
No, we did not. Okay. So we did not plot the pole zero yet, right? So can you check? Can you use the S? So we want to plot the pole zero of that filter, but it is in continuous time filter, so you cannot use Z plane, because Z plane is for discrete time pole zero plot. So I'm actually searching for pole zero plot for a continuous model, for a continuous time system. So this is a toolbox. This is a toolbox. It's a plot. It requires the system. don't think we can use the Z plane. But let's try with the BNA coefficient. Let's try this. So all the poles, there are 5 poles, right? All of them seems to be on the left hand plane, which is good. But how about the other poles? It's supposed to have 9, 2n minus 1. It's supposed to have 10 poles. 0 to 2n minus 1, 0 to 9. So it only shows the left hand 5 left hand plane pole. Okay. So it is not working. We do not know. It seems that apparently it is stable because it only plots the left hand plane pole. So can we think about other way? For example, FIR filter. Can you think about some other way to design the filter? FIR filter. For FIR filter, what are the specification required? What are the specifications required for FIR filter design? Tell me.
Pass band and stop band ripples and omega P and omega S.
Okay. So let's see that if we have an example on FIR filter or not. Okay, so we have a built-in function for FIR filter as well, where we can see that we can use this FIR1 built-in function. Okay, FIR1 means it is an FIR filter using 1 means window design technique. Okay, so FIR1, if you just give the order of the filter and omega C, then it will give you this H. H means the impulse response of the filter. For FIR filter, you also know that this H is actually same as BM coefficients, right? So that means this is B. Okay. So if you do not mention anything, the filter type, then it will by default design a low pass filter. If you do not give any type of a specific window function, then it will by default use rectangular window function. Okay. There are options for window function mentioning as well. Let's say that you give the filter type, whether it's a low pass, high pass, band pass, or band reject. And then you can also mention the window function as well if you want to use a specific window other than rectangular window. Okay, so let us try. Let's go back to MATLAB and let us try FIR filter now. Okay. So we said that we can use an H to find out the FIR filter function. So we have still the same N on omega C. Now for IIR filter, you can use a order which is much lower. Okay, but for FIR filter, the order should be much higher. Okay, typically, because FIR filter with the same order as IIR will give you very bad response, filter response. So let's take the order something big. It's a 64 order. And then find out the H, the impulse response. And we know that H is equal to same as B. So we say that B equal to H. And your A should be equal to 1, right? Because A means we're talking about A0 only. For FIR filter, there is no A1, A2, A3. Okay, so now we can use the same B and A coefficient to apply the filter, or in this time first we take a look at the frequency response of the filter. Now it is an FIR digital filter, so it is, we call it FreqZ to plot the frequency response and check that whether we have designed an appropriate filter or not. Okay, so see that at point 1 we have minus 6.64 dB. So it is in decibel, so which is supposed to be minus 3 dB, right? But it is minus 6. Okay, so at a cutoff frequency it is supposed to be 70.7%, or in decibel unit it's supposed to be minus 3 dB. But here it is minus 6 at point 1. And you can see that there are a lot of ripple in the stop band. Can you see that? Lot of ripple. Okay, so can you measure the ripple? How much ripple we have? How much ripple we have here? So if you think about from the peak to peak ripple is, let's say, around minus 60 and minus 100, right? Approximately 40 dB. So what is the stop band ripple we can say here? It is approximately 40 dB, right? So that is our AS. How about the passband ripple? Is there any passband ripples? Apparently. But if you zoom in, we can see some of the ripple. Okay, so there you go. You see there is a very small amount of ripple in the passband as well. Okay, can you see that? Now what is the peak to peak ripple here? Can you say it is 0.02, 0.01, and then minus 0.01? So can you say that our passband ripple RP is equal to 0.02? Can you say that?
Yes, sir.
Yes.
Okay. So apparently, and also you can think about the phase response. Is not it linear, zigzag, but linear, right? Straight line. Yeah.
Yes.
So this is a FIR filter supposed to have linear phase response. Okay. Again, we are concerned about our filtering application of the filter. Design filter seems to be well, but whenever we are applying, seems to be there is not is a problem, right? So let us try now this one as well. So again, we apply this filter function on B and A coefficient. So now we have a different B and A, which is for the FIR filter. Okay. And then we do the same thing. We plot all the 3 signals in one window. Okay. Now we have plotted, first we plotted the, instead of time domain, we have already plotted in the frequency domain. Okay. So I think that we have been able to find out something, right? What do you expect now? What do you expect? Better result? Some good luck? Good luck? Yeah? Yeah.
Yes.
Okay, so let's plot in the time domain to see whether we have been able to extract those ECG signal. So still it's noisy, but it was not there before, so we can somehow find out some of the peak. You see, these are the peaks during ECG, but we still cannot find out exactly the QRS complex point properly, right? Still very noisy. Still very noisy. So that means that we can improve the filter, right? We can start using a different window function. We can increase the order of the filter and see that if there is any luck or not, right? So we can actually try a different way. Okay. So one thing that you should understand, when you are applying the filter, your order of the filter is actually a delay. Okay, so 64 means your signal starts 64 samples late in the filtered output of the filter. Okay, so you have to adjust that delay as well. Otherwise, when you are going to do the correlation, because correlation in time domain takes into account about the phase shift of the signal, although the signal, they have similar characteristics, but because of the phase shift, you know, the correlation or similarity will be much lower. So you have to consider that as well, the delay. Okay, so you can, let me show you the delay. So what was the order of the filter we have taken for this FIR filter? Do you remember? Was it was 64? Okay, if you remember what was the order of the filter, see,
n equal to 64.
yeah, so there's supposed to be a 64 samples delay. Okay, let me show you the delay now. In the filter signal, there's supposed to be delay. Okay, so this is the delay basically. I mean, more specifically, you know, you see that there is a delay, and that delay part, it is actually 0. Okay, so this is one delay at the start, and then there's supposed to be delay at the end as well. Difficult to zoom in. So at the end, there's supposed to be some delay as well. So overall, there will be 64 sample delay. So you have to adjust that delay. Basically, at the beginning, this is the delay of around 32, and at the end there will be another 32. So total 64 delay, sample delay. Okay, so you have to use that part carefully, so that when you are going to do the correlation analysis, you are actually ignoring that phase shift. Okay, you have to get rid of that phase shift when you are going to calculate the correlation coefficient. That's the point that I'm trying to make. Okay. Now let's say the next question is whether you have been able to improve the signal to noise ratio or not, right? This is your now the question. So what was the signal to noise ratio before, and what was the signal to noise ratio after? So that means you have to define the noise first. So what is the noise here? You have a clean signal and you have a noisy signal. So what is the noise? So you can find out the noise if you, from the noisy signal, if you subtract the clean signal, right? This is supposed to be the noise. Okay, so this is supposed to be noise before the filtering, because it is clean, right? Calculate the SNR. The SNR is supposed to be signal and noise. Okay, so what is the signal? The clean signal is this clean, and what was the noise before filtering? This is the noise. Okay, so this is supposed to be the SNR. So what was the previous SNR before removal of noise before filtering? It is minus 12 dB. It says, right? Now what do you expect the noise to be after filtering? Now you consider the filtered signal, right, with respect to noise. So let's say it is noise 2. And then what is going to be the SNR? SNR will be, this is the SNR2. It's filtered, okay? And now using the noise too. So previously you had minus 12 dB SNR. Now we have minus 2 dB. Has it increased from minus 12 to minus 2? Is it an improvement or not? Yes, it was
Yes,
minus,
sir.
remember, minus 12 dB. So now it is minus 2 dB. So 0 dB, what does 0 dB SNR means? That means signal and noise power, they are same. That's why you are coming out log 1 is 0, right? So let's say what is 10 dB means, or what is 30 dB means? That means the signal power divided by noise power is that log of that part, right? So negative, why it is coming as negative decibel? Because your noise power is still higher than the signal power. That's why you have a log of fraction is negative. But one thing that we have understand that before even filtering, the noise power was even higher, right? So that's why it was minus 12 and now it is minus 2. So there is an increment, I mean enhancement or improvement in terms of the signal quality. However, the signal is still not, as desired one, right? It cannot be used at the moment, the type of the signal that we have retrieved after filtering. So there is an opportunity to improve the filtering process. However, if I say that for the project requirement, is it good enough? Yes. So far, what we have done, all the step-by-step process, and with these evidence, we can say that we have done well. We have not done pretty bad. Okay. So that means from the project point of view, this is not a bad one. Okay. Because we have been able to reduce some kind of noise. Maybe the signal is still not usable for our purpose, but we understand the filtering process. We have been able to apply the filtering and we have been able to evaluate the performance of the filter. Okay, so that is the minimum requirement of the project. Next is that you try with different order, different window function. Okay, and you try to improve the filtering performance. You try to improve further the signal quality so that the signal somehow looks like an ECG, not any other signal, right? Okay, so and let us again talk about the other part of the performance parameter. Let's say coherence, right? So coherence, it is MS coherence, I believe. Yeah. So coherence actually gives you, I mean, correlation at all the point, at different point, whatever the length of the signal. So therefore, we should take the mean value of coherence. Okay, mean value of the coherence. So what should be the coherence? Again, the coherence supposed to be before filtering. It is supposed to be between raw and between clean. Raw and clean, right? So previously the coherence value before filtering, it was 0.1656. After filtering, that means with clean signal, but this time with filtered, is 0.359. Okay, so it is the correlation in frequency domain. But coherence wise, it seems that which one is better, before filtering or after filtering? What the value suggesting? What is the
So
value?
before filtering,
Before filtering seems to be better, right? Because the coherent, the similarity is supposed to be higher after filtering, but it somehow comes as lower. Okay, so this is maybe because of the delay. Okay, maybe because of the delay, or you have to further improve the filtering performance. Okay, another part was RMSE, right? Root mean square error. So RMSE was before filtering was between raw and clean, right? So before it is 0.7567. What do you expect the RMSE after filtering? Should it increase or decrease the error?
Decrease.
So has it decreased after filtering?
Yes, sir.
Okay. So 0.75 error to 0.36 error. Okay, it seems to be decreased. Right. What else? Coherence, correlation, right? Now, correlation. So correlation is correlation coefficient between before filtering remember the correlation in time domain, it takes into account of the phase shift, and because of the delay element order of the filter, there is a delay, so it will take that. So before filtering, what is the, so you can take this value as the correlation coefficient value. Okay, so 0.2287, what does that mean? 22.87% of similarity between the noisy signal and the clean signal before filtering. Okay, now same thing for after filtering. The one thing we have noticed that each time we're actually using the clean signal as the reference, right? So we are always comparing with the reference clean signal. But it has become negative 21.76%. Okay. So before filtering, it was a positive correlation. Now we have a negative correlation. But even think about negative, why is it is actually, it has decreased, right? Negative correlation is also correlation, but the value is also decreased. Okay, it's supposed to increase. Okay, the similarity is supposed to increase. Okay, so and that is because of the, as I mentioned before, that is because of your presence of your delay in the signal, in the filter signal, because there is a delay, so there is a phase shift. Phase shift will make the correlation even worse. Okay, so that is the one thing that you have to see. What else? We have talked about the 4 performance parameter, right? So this is how you have to actually approach in the project. Okay, so you see that we tried IIR filter first. IIR filter frequency response looks good, but apparently the application, when we apply the filter, there was a huge problem, right? We found that. And then we tried with FIR filter. We found that there is some lag with FIR filter, but it is exactly not as expected. The signal certainly has improved, but it is not good enough to be usable for ECG signal characteristics analysis. Okay, so that means there is a way. But what I have done so far, this is the minimum requirement. Okay, this is the minimum requirement. So if I do all the things correctly, if I follow the report template, the presentation, the demonstration template, and all the MATLAB file that I have found, if I properly upload, then as a student, I expect that out of 25, although the filter output is not very good, but I expect that I will get 20%, 20 marks out of 25. So that is 80%. So that is the minimum requirement of this project. Okay, so I expect with this filtering performance, I still expect as a student to get 20 out of 25 if I properly upload everything, if I submit the report according to the template and everything. Okay, if I follow the instructions. So that is overall the idea about this. Do you have any question? No. You think about it. So it is not a time bounded exam, right? You will get like at least 1 week to work on. So that means you should do some literature review on you should see some tutorial on YouTube. You some online materials, you go through some of the examples. Okay, so now you have option. It is not a final exam or time bounded exam where you have to answer everything. That is the, I mean, reason, because through this project you are actually addressing some complex engineering problems. Okay, some of the attributes of the complex engineering problem will be addressed. So one of them is depth of knowledge, depth of analysis that you are going to do. You know, there are some conflicting requirement you will find. For example, if you increase the we have seen the conflicting requirement while choosing the window function. Remember, there was minimum stop band attenuation AS and there was transition bandwidth. Was not is a conflicting requirement. If I get better result in terms of transition bandwidth, then I lose in terms of stop band bandwidth, stop band attenuation. Remember that the dilemma
Yes.
in choosing the in selecting the proper window function. So that was a conflicting requirement, right? So again, you increase the order of the filter, there is a delay, higher delay. So also this is another conflicting requirement. So this is the project given to you to address all these attributes of complex engineering problem. Okay, and there is a familiarity of issues as well. For example, there are issue that you are not familiar with before. For example, EEG signal, right? Now for the sake of the project you have to do a bit of literature review on EEG signal, background, theoretical background on EEG signal characteristics, how the signals are acquired, how the signal actually properties looks like. So what is expected in EEG signal, what is not expected, and all the stuff. So this is very different from the other, meet, final, and class test. This is where you can actually explore a lot of things. Any other question? Yes, if you do, you know how to export your filter design toolbox into a code? Do you know that? You can do that. There is no problem with that. I don't mind, even if you say that, okay, I'm not going to use the code, built-in code, I can write my own code. So you can do that also. Okay, let's say there was a built-in FIR1 filter, right? You can use your own filter function if you want. You can make your own. So that is not a problem. Whether it's a design tool, the problem is that whether you are addressing those requirement or not. Okay, that is the issue. So your design is open-ended. You can use any design tool. Whether it's a code or graphical user interface, or you can use your own MATLAB built-in, user-defined function, does not matter. আর কোনো প্রশ্ন আছে তোমাদের? Rubaiyat Faruqi, Anthony, Shruti, Ananna, Abdul Rahman, Akib, Osman,
Yes, sir.
Sahid Alam,
Present, sir.
Nadim Mahmud, Fardin, Wafuz Zoha, Sumaya, Afran Farooq,
Present, sir.
Taremun Arifin, Nafisa Tasnim, Tasfiya Hassan Faiza,
Present, sir.
Imtiaz Abedin, Sajid Ahmed,
Present, sir.
Oishi Benazir, Mahmud Sajjad, Tanzima Taharin, Hasibul Hassan, Abhishek Dash, Mukti,
Present, sir.
Obi Shah,
Yes, sir.
Anika Saima,
Present, sir.
Haji Wafa,
Present, sir.
Khalid Mahmud, Sajid Hussain, Samara Islam,
Present, sir.
Roman Khan,
Sir, Tajid Hussain present, sir.
Yasin Altaf,
Yes, sir.
Nan, Tanzir,
Yes, sir.
Sajid Jafri,
Present, sir.
okay, thank you.